This is the 2016 Level 2 Waves exam. For this video I'll be working through question 1. Question 1. Light. Tim was looking into a convex mirror ball in his garden. Standing behind a small plant, he noticed that when he looked at the reflection of the plant in the convex mirror, it appeared smaller than it really was. Complete the simplified ray diagram above, not to scale, to show where the image of the small plant would appear. So for any waves exam, you are going to need a ruler. Right, so this is a convex mirror, which means the focal point will be behind the mirror. And so we'll do the in parallel ray first, which means in parallel out through the focal point, and as you can see the rays diverge. So that's the outgoing physical light ray, and then in through the focal point, which is, I'll just double check, yeah, that means that's going in through the focal point, which means it needs to go out parallel. If we just do that out parallel, so these are the outgoing light rays. So that's the physical actual light rays if you use the ray box. To find the image, we just backtrack those outgoing light rays, just do the dotted line. I don't know if I did that right, it's a little bit too far above, that's alright. Dotted line, and where they meet you'll get an image, and as we can see it's upright, it's virtual because the image forms behind the mirror, and it is diminished. Question B. Tim uses a convex lens to create an image of a small plant. The convex lens has a focal point of 40 centimeters. Draw two appropriate rays on the diagram below to show when the image of the plant would be formed. So this is a bit of a doozy because it's gone from mirror to lens, and this is your typical magnifying glass lens, so it's not too particularly difficult. It goes through a convex lens. We just go in parallel. We'll go in parallel first and then out through the focal point. So in parallel, out through the focal point. And we'll go in through the focal point on the other side, if we can do that. Oh no, we won't. What we'll do is we'll go in through the focal point on this side. What am I talking about? In through the focal point on this side. And then we go out parallel. Right, so there's one thing I'm missing, and that is the direction of the light rays. I need to put wee arrows on the light rays. You can put them all the way down it, doesn't matter. Yep, so I've drawn two rays. You could draw another one that goes straight through the pole of the mirror, which is essentially the center of the mirror, and if you look at that, it lines up exactly where the other two rays meet, but it only asks for two, so only give two. And then draw the image in the correct position. So I'm going to use my ruler for this. If we draw the image here, there we go, and we draw the arrow to show that it's upside down. In this case it's a real image because you can project it onto a screen, and it is diminished. If I can, yeah, it is diminished. Right, next question. The images produced by the convex mirror and the convex lens are quite different. The convex mirror produces a virtual image, convex lens produces a real image. Explain how Tim could detect the difference between the two images. So let's answer the first bullet point. Bullet point 1, real, okay, I'll just write it down. Real appears rays converge. So a real image appears when rays converge, and a virtual image appears when the rays diverge. V-E-R-G-E. And convex convex lenses always produce virtual images because it's a diverging mirror. The rays always spread out. Diverge just means spread out and never meet again. Convex lens will always produce a real image if the object is in front of the focal point, and it'll produce a virtual image if it's, so when I say in front I mean behind, so it'll always produce a real image if the object is, so here's the focal point, here's a lens. If the object's behind it, it'll always produce a real image, so you can project onto a screen. If it's in front of the focal point, it'll produce a virtual image because the rays will diverge on the other side, meaning they will never meet. So you have to backtrack, and then if it's at the focal point, you get no image at all. And if you're at the focal point for any mirror or lens, you'll never, except for a convex mirror, concave mirror at the focal point, no image. And take that back, it's only concave and convex. So concave mirrors and convex lenses, if you're at the focal point, you'll get no image. Anyway, I should probably move on. Explain how Tim could detect the difference. Virtual images can't be projected onto screens. So virtual images cannot be projected onto a screen. And secondly, have I spelled that right? I think so, that looks weird. A screen, and all real images are inverted, and that's just I don't know, it's just sort of something that happens. A concave mirror is the only mirror that will produce a virtual image, and only produces a virtual image when it's I suppose not between the mirror and the focal point, so behind the focal point, if that makes any sense. Convex mirror only produces virtual images, and a concave lens only produces virtual images, and a convex lens will only produce real images if the object is behind the focal point, so not between the focal point and the lens. Right, moving on. Tim places a small 10 centimeter plant a distance 60 centimeters from the convex lens with a focal length of 40 centimeters. So still using a convex lens. I'm just going to quickly sketch this up so I can think about this in my head. Here's my axis, here's my convex mirror. He's placing a plant 60 centimeters. There's plants somewhere up here, and it's about this high, and the focal length is here. If so this is 60 here, it's 10 centimeters tall. It's not exactly to scale. Just we could sketch this out, figure out where it's going to be. It's going to look something like that down there, and then over there. There we go. So we know that the image is going to be upside down. It's going to be real, and it's probably going to be similar height, but not exactly the same height. It could be possibly bigger, hard to tell. Although my guess it would be smaller. Anyway, I don't even know until I figure it out. Right, let's go. We've got the focal length equals 40 centimeters. 3SF. I'm going to stick with centimeters because mirrors seem to be, or optics, you can use centimeters, it doesn't change much. Equals 0.6. Oh, I did it in meters beforehand though. 60 centimeters, and HO equals 10 centimeters. I normally prefer meters, but try doing centimeters today. DO equals question mark, because I'm going to try and find it. Ask for the distance of the image between the image and the lens, and the height of the image. So I'm trying to find DO, and I'm trying to find HO, the height of the image. Height of the object, height of the image, same. Oh no, HI. I have HO, height of the image, equals question mark. So first and foremost, I'm trying to find DO, because 1 over F is equal to 1 over dO plus 1 over di. Order doesn't matter. Right, in other words, dO is equal to 1 over f minus 1 over di. Yep, but now we need to take the inverse of that. I'll put inverse, it just means take 1 divided by this whole entire answer, whatever that answer is on your calculator, and that'll give you dO. If you plug that in, your focal point should be positive because it is in front of the lens, and your distance to the object image is positive because it's in front of the lens. If anything's behind the lens, it means your numbers need to be negative. Right, so that equals 120 centimeters. Next one, find the height of the object image. So di over do equals hi over ho. It's going to be easy if we flip these over. In other words, do over di is equal to ho over hi times both sides by the height of the image, which will give me hi times, cross this out. Right, there we go. And we'll put some numbers in just so we know what we're doing. So hi 10 centimeters times 120 over, so I'll just put centimeters, I don't know why I'm putting centimeters, over di 60 centimeters. And that equals, that's 2 times 10 is 20 centimeters. And they've given me 3SF for everything, so this needs to be 20.0 centimeters, and that is 3SF as well. And I better double check my, yeah, that's it.